Hello everyone, hope 2025 is treating you well so far. If not, don't worry. Looks like Santa came late to AASPI this year. We've got a treat for you all. No, we're not handing out free ice cream to our sponsors. Instead, we're introducing an exciting new attribute into AASPI. But is it new? Let's rewind to 90s where I've heard dial-up internet was a thing. Dennis Neff, working at Philips, developed an attribute DQ, which stands for Distance and Quadrant. Philips has been using DQ to produce some exceptional studies over the years, and now it's being quoted by me to make its grand entrance into AASPI. The DQ trace method is a new approach to seismic interpretation. This attribute that transformed traditional wiggles into block sections that actually mimic porosity logs. So imagine viewing porosity on seismic. Let's be honest, traditional seismic interpretation isn't always easy. We often struggle to distinguish between fluids and rock layer. It's like trying to separate chocolate chips from a cookie. The DQ trace method combines elements of AVO analysis and quantitative interpretation to provide clearer insights into our reservoir properties in traditional seismic interpretation. We often struggle with limitations in data clarity, particularly when trying to identify hydrocarbons and characterize the reservoirs. Some of the common challenges we have include unclear layer boundaries, difficulty distinguishing fluid contacts, and some ambiguous thickness. So the distance and quadrant attribute method addresses how these challenges can be addressed by how we process and display the seismic. Alright, so how does it all work? The first step in the DQ trace workflow is input data preparation. We use partial, near, and far stack traces. Near stack from 0 to 10 degrees, far from 20 to 30 degrees. Why these angles? Because they help us optimize signal to noise ratio while keeping an eye on acoustic impedance changes and fluid effects. The near stack is all about lithology, while the far stack captures fluid-related AVO effects. Now, this is where things get interesting. Phase angle analysis. Imagine taking your seismic trace, rotating at different angles. We apply phase rotation of 45, 90, minus 45 to assign quadrant numbers and extract the minimum amplitudes at each time sample. The result, we turn every seismic wiggle into an equivalent peak or trough, ensuring no valuable information gets left behind. On this slide, we can see the before and after magic. Traditional sinusoidal traces often leave us guessing, but with the DQ trace, we get a crisp, blocky format that enhances layer boundaries and provide consistent amplitudes within the lithological layers. Sinusoidal transform to block, giving consistent amplitudes within the lithological layers, which is a good representation of geology. This transformation, when we look at the same data in the AVO, crossplot on the right side. The DQ process pushes the gas and the data points, which are the pink diamonds, kind of outward on the circle at 4 specific positions, and this creates tighter clusters than the original scattered kind of more torpedo shape of conventional seismic data that is shown by the pink circles. This clustering makes identifying gas sands much easier to identify and map. On this crossplot, you can see how the DQ data points migrate from distinct clusters, which make it easier to identify different lithologies and fluid contents. We can see how gas sands are pushed outwards, which are in green color, make it easier to visualize gas-water contact on seismic. This is where it gets really cool. TQ trace has an uncanny ability to mimic porosity logs. It's not magic. It's pure rock physics. By leveraging the relationship between acoustic impedance (VPVS) and porosity, we can derive porosity estimates directly from seismic data. So imagine you can see porosities by just looking at the seismic. Now, the infamous tuning effects. Every interpreter's nightmare. But guess what? The TQ method handles them brilliantly. It provides optimal performance between a quarter and half a wavelength, giving us accurate thickness estimates even in thin beds. Let's take a quick tour of AVO classes. If you look at class 3 traditional gas sands here, the TQ trace method consistently differentiates wet sands with gas sands. Look at the seismic amplitudes and then compare it with the TQ display. How beautifully the water and gas contact is highlighted. It's so amazing. If you didn't get a chance to meet me at the annual meeting, here are the QR codes to my contact info and LinkedIn. If you want to know more about TQ, check out our website. I hope you're as excited to check out TQ as we are. So stay tuned and goodbye.